All right, so for number 2, this question says to explain the process of osmosis. So osmosis, to define it, it would be the diffusion of water through a selectively permeable membrane. And this diffusion will go from an area of high water potential to low water potential. So kind of drawing a visual of this here. See, we have a membrane here. We have a solution. And say we have a concentration of solutes in here that can't pass through this membrane. And so osmosis is the water inside A, we'll call it, will want to go over to side B. So it will begin to look more like this. Okay, so now to explain the difference between osmolarity and molarity. Osmolarity has to do with the amount of particles of solute per liter of solution, where molarity has to do with the molecules of solute per liter of solution. So let's take NaCl for example. In a solution, NaCl, in the solution of water, NaCl is going to separate into sodium and chloride. And so this right here will equal a 2 osmol solution of NaCl because there are 2 parts. Where with molarity, this NaCl will become a 1 molar solution of NaCl. That's how osmolarity differs from molarity. So when talking about the differences between osmolarity and tonicity, we know that osmolarity is talking about the solution. So we know when talking about the amount of particles per liter of solution, we can use different words to describe it. We can use these words iso, osmotic, hyper, osmotic, and hypoosmotic. And these prefixes mean same, more, and less. And these terms are talking about the amount of particles in liters of solution. And so with tonicity, we can use these same prefixes to describe tonicity, but tonicity specifically talks about the effect on the cell itself, the tone or the stretching of the membrane of the cell and what it will look like based on the solution that it's in. So if we see an isotonic cell, I'll go ahead and draw a little picture here of a solution, and we will have a cell inside of a solution. And so what happens is if we have the same concentration here inside the cell and outside the cell, there won't be any movement that will change the size of the cell. So this cell right here will be isotonic. When we think about hypertonic, I'll go ahead and draw another picture here. When we have a cell in a solution and there is more solutes outside of the cell in the solution, then the water is going to want to leave the cell and go towards the outside where there is more solute. So when that happens, the cell is going to shrivel up and become smaller like this. And that will increase the amount of water outside of the cell. When we talk about hypotonic, that is the opposite. So with this cell, we can draw a high concentration of solute in the cell. And so what will happen is the water from the solution will want to enter into the cell to go towards the high concentration of solute. And that will cause our cell to get very, very big and filled with water. Okay, so now to explain a little bit more about osmolarity and tonicity and how they differ, we're going to answer this question: how can a solution be isoosmotic but hypotonic to a cell? And so what I'm going to do to kind of explain this is give the example of urea. And urea is something that is permeable. So what we will do is I will draw a little representation of an isoosmotic solution, meaning the same. So this will be an isoosmotic solution, and what we will do is we will insert a cell into the solution. So once we have this cell in the solution here, these particles of urea will go down their concentration gradient from high to low and enter into the cell. And once they enter into this cell, we will start to have a higher concentration of urea compared to outside. And with this higher concentration, now we know through osmosis, in order to re-achieve homeostasis, the water from outside the cell is going to travel inwards towards the higher concentration. And so when that happens, we will have the cell become larger. It will get much bigger to accommodate for that water that's entering into the cell. And this will cause the cell to be hypotonic. So we start with an isoosmotic solution, and we know that the urea will travel into the cell here in step 1 because of its concentration gradient. And in step 2, the water through osmosis will travel into this cell with a higher concentration of urea, causing this cell to swell here in step 3. All right, so for part 2 of this essay question, we're going to talk a little bit about resting membrane potential. So if we come down here, RMP, resting membrane potential, is equilibrium of concentration and electrical gradients. So to kind of give a visual of this here, we'll go ahead and draw this tank, and we'll have a semi-permeable membrane. And this membrane will only be permeable to potassium. So say we start with lots of potassium chloride here on our right side. And so due to potassium's desire to go from its high concentration to low concentration, in this concentration gradient, we will have some potassium come on over here. And so that will change the concentration of potassium. We'll want to come to this side. And so when that happens, we will have an increase of negative charge on this side, an increase in positive charge on this side. And so due to this increasing negative charge on, we'll say this is side B, this increasing negative charge will cause this potassium to come back over to this to side B in order to equal these positive and negative charges. And so when the motion of the concentration gradient going this way with potassium and the electrical gradient bringing it back this way, potassium is at an equilibrium, that is what we call the resting membrane potential. And so when thinking about the resting membrane potential, there are a few things that come into play that cause this resting membrane potential to happen. And so what we'll do is we'll start by drawing a cell here, and we will label a few different things. So first we have the sodium potassium ATPase pump here that brings out 3 sodiums outside of the cell and 2 potassium ions into the cell. And here we will also have the leak channels for potassium here and here. And so what happens is we have a high concentration of sodium outside of the cell due to this pump, and a low concentration inside of the cell. Also, because of this pump, we will have a higher concentration of potassium inside the cell and a lower concentration outside of the cell. And so because of these leak channels, we will have potassium wanting to go from its high concentration to low concentration. It will leave the cell this way. And so as the potassium leaves the cell, that concentration gradient will start to reach equilibrium. But just as we talked about before, that potassium will be sucked back in due to that electrical gradient that will cause that equilibrium. And another thing that I should have mentioned about the inside of the cell is that the inside of the cell will overall be more negative and the outside of the cell will be more positive due to the negatively charged proteins that are stuck within the cell. And so this potassium here will get brought back into the cell because of this negative charge, the prominent negative charge that is inside of the cell here. So when talking about resting membrane potential, the two big factors that play into the magnitude of this RMP are the concentration gradient of the ions that are involved, as well as permeability of the membrane. So with different ions and different concentrations of those ions, we could have a different magnitude of a resting membrane potential depending on which ions are moving in and out of the cell, and the permeability of the membrane will also determine that. So now we're going to talk about two different equations here. First, we have the Nernst equation, which gives this value E, which is the equilibrium potential. So we calculate this value with negative 61 over Z, which is the charge of the ion that we're working with. So each one of these equations is only for one ion. And so that is multiplied by the log of the concentration of the ion going into the cell divided by the concentration of the ion going out of the cell. So say if we're talking about sodium, the charge of this ion is going to be +1. And so once we're able to solve for this E value here, we will go down and to determine what is called the driving force. And so the way I like to think about the driving force is it is the number that kind of describes the want of the ions to move either in or out of the cell. So we will take this E value that we just calculated with the Nernst equation and plug that in here. And we will take the V, which is the voltage of a specific type of cell, and plug it in here. So for a neuron, we talked about in class, the average voltage is around -70 millivolts. And so depending on the cell, we may have different values, but we can assume for a neuron that we would start with -70 minus the value that we get for E. And so this driving force, like I said, talks about the want for ions to move. So say for sodium, if we calculate a driving force, which will always be on the inside of the cell, a driving force of -143, just throwing out a random number, because this sodium is positively charged, it is really going to want to go into the cell in order to reach an equilibrium with this highly negative charge. Say we were to calculate the driving force for potassium, and if that was a +15, then we know that this potassium with this positive on the inside is going to want to leave in order to decrease this positive value to reach an equilibrium once again.